I have no idea why my camera turned into a pumpkin there, so hopefully it's not too much of an inconvenience that you're having to watch a second video. But let's proceed. I want to talk about the completeness property of the field of real numbers. And this gets into a field called topology. If I've motivated some of you to go on in mathematics, or if you were already planning to go on in mathematics, I hope you get a chance to take a topology class. We'll be offering it next semester, and it doesn't really require anything except calculus classes. But the subject of the real numbers is an interesting one, because the real numbers have the property that between any two real numbers, there's another real number. But also, between any two real numbers, there is a rational number, a fraction, a continuing, a repeating decimal. And between any two rational numbers, there's an irrational number. And there are, as a matter of fact, between any two real numbers, there are infinitely many rational numbers and irrational numbers. So they are put together in there densely. And that actually is the mathematical phrase for it, that the real numbers have as dense subsets the rationals and the irrationals. And it's exactly that property, that between any two real numbers, there's a rational number and an irrational number. And if you like open and closed sets, the smallest closed set that contains the set of rational numbers is the whole set of real numbers, from minus infinity to infinity. And if you're not sure why that one has to be closed, take topology and you'll find out. But the completeness axiom is exactly what I just stated. Let's see if we can progress through it. Okay, suppose that E is a non-empty set in the real numbers. Okay? And suppose that E is bounded above. Okay? Then we know that E has, I don't need N, E has a sup. It has a supremum. Okay? Now you remember a couple of times during the semester I've proven, one time last time, but I've proven that the square root of 2, if it exists, is an irrational number. But does it exist? And in order to prove that, we need the completeness property for the real numbers. So let's proceed with this. Let's show that the square root of 2 exists. And in order to do that, I want to start with a lemma. Okay, the lemma is this. Suppose A and B and C are positive real numbers, and A is less than B squared, which is less than C. Okay, so just in general. Has nothing to do with the square root of 2 right now. Just suppose I've got 3 positive real numbers, and A, between A and C, is B squared. Okay? Then there exists X and Y in the positive real numbers such that x is less than b is less than y, and a is less than x squared, and c is greater than y squared. So what does all this stuff mean? Well, it means here's a, here's c, and here's b squared. Okay? And what we're saying is that I can find x and y so that a is less than x squared, but x squared is less than b squared, b squared is less than y squared, and that's less than c. So in other words, what I've done is I've stuck an x squared between a and b squared, and I stuck a y squared between b squared and c. That's what I've done. And I want to show that that's possible to do. So here's the proof. We first show that y exists. So I have to show that both x and y exist. We'll start with a y. Okay, so let epsilon. Now this is going to seem really synthetic, but the reason it's going to seem synthetic is because it's really synthetic. Epsilon is going to be the smaller of these two numbers, 1/2 or c minus b squared over 2b plus 1. Huh. Why that number? And you'll see it pop out later, and you'll see why that number. But notice that epsilon is greater than 0 because c minus b squared is a positive number because c is greater than b squared. B is a positive number because it's bigger than x and x is bigger than 0. So 2b plus 1 is a positive number. So c minus b squared over 2b plus 1 is a positive number. Of course, 1/2 is a positive number, so epsilon is greater than 0. So then epsilon is greater than 0. Cool. Now I'm going to define y. Let y equal b plus epsilon. Now, since epsilon is less than 1, why is epsilon less than 1? Because regardless of what the second number is, if this number is bigger than 1/2, then epsilon is 1/2. So epsilon can't be any bigger than 1/2, so epsilon is less than 1. Hence, as we learned not long ago, if I multiply both sides of this by epsilon, epsilon squared is less than epsilon. Okay? Now let's do some arithmetic. Therefore, y squared, what's y squared? It's the square of this number. It's b plus epsilon squared, which you have foiled many times. That's b squared plus 2b epsilon plus epsilon squared. Okay, which is less than what I would get if I replaced epsilon squared by this bigger number, epsilon. So this is less than b squared plus 2b plus 2b times epsilon, sorry, plus another epsilon, out of which I can factor an epsilon. So this is equal to b squared plus 2b plus 1 times epsilon, okay, which is less than or equal to, less than or equal to, or less than? Less than or equal to b squared, copy, copy, plus 2b plus 1 times c minus b squared over 2b plus 1. Which is equal to, now the 2b plus 1 on top, 2b plus 1 on the bottom, and the people all said, poof, right? I hope you said poof. So when those kill each other off, I've got b squared plus c minus b squared. And b squared minus b squared, thank you. So that's equal to c. And so y squared is less than c, which takes care of this part. Let's take care of the other part. Now, there are people who believe that when we die, we just go to sleep for a while and then everybody gets resurrected to go to heaven at the same time. Paul says that that's false, but pretend that this is soul sleep for a moment, because I'm going to pause you, I'm going to go get some more squirt, and I'll be back. You see, being asleep and then being resurrected is not all that bad, but that's not the way it happens, because Paul said, absent from the body is present with the Lord. So I'm not the Lord, but I think you get the analogy. Anyway, let's show that X exists. Let X be b minus epsilon, where now I'm going to define epsilon to be b squared minus a divided by 2b. Then, once again, epsilon is greater than 0, because we're given that a is less than b squared, so b squared minus a is positive. B is in the positive real number, so the bottom is positive, so the whole thing is positive. And let's do the arithmetic. X squared is equal to b minus epsilon squared, which FOILed is b squared minus 2b epsilon plus epsilon squared, which is greater than b squared minus 2b epsilon plus 0. Here I'm adding something positive, so if I ignore the positive thing, that's certainly greater than this. Okay, cool. And so now let's plug in what epsilon is. That's equal to b squared minus 2b epsilon. The two b's, top and bottom, poof, and I get b squared minus minus a. So what have I shown? That x squared is greater than a, which is exactly what I had to prove about x. And that ends this. Okay, theorem. How can I use this to prove that the square root of 2 exists? Well, it's not too hard. Let E be the set of all x in R such that x is greater than 0 and x squared is less than 2. since 1 is in E, E is not empty, right? 1 is greater than 0, 1 squared is less than 2, so there is stuff in here because it includes 1. So it's not the empty set, so it satisfies a condition for the completeness axiom. E is bounded below and above below by 0 and above by 2. Since x is greater than 0 for everything in E, so it's bounded below by 0, it's bounded above by 2 because 2 squared is 4, so that's not in here. It's bigger than everything in here. So it's bounded above and below, so E is bounded. All right. Now, because it's bounded, let B equal the sup of E. We will show that B squared equals 2. So B is our candidate for the square root of 2. And we'll do it by contradiction. If B squared is not 2, then it has to either be less than 2 or it has to be greater than 2. So let's do case 1. B squared is less than 2. Well, by the lemma, with B equal to 2, with C equal to 2, let's use the same letters as we used before, choose Y less than B greater, hang in there, Y greater than B, such that Y squared is less than 2. Now, why can we do that? We can do that, okay? Or Y squared is less than 2. All right, so taking C to be 2, we're just doing it literally off what we just proved in the lemma. Okay? Then Y lives in E. Y lives in E because Y squared is less than 2. Y is certainly greater than 0. So Y lives in E, so it's less than or equal to the upper bound, the least upper bound, which is B. But how did this start? This started with Y greater than B. So that's our contradiction there. So case 1 does not happen. Let's see if we can rule out case 2. Okay, here comes case 2, which of course is B squared is greater than 2. See if we can rule this out. By the lemma, this time with A equals 2, choose x less than b such that 2 is less than x squared, which we can do by the other half of that lemma. Now, once again, in this case, x is not an element of E, right? Because what is E? X squared has to be less than 2, 2 less than x squared, so x does not live in that set. So x is not in E, but let's pick a W that is in E. Then W squared is less than 2 is less than x squared. So that implies that W squared is less than x squared. I'm sorry, that W is less than x squared. For all W in E. So x is an upper bound. For E. Okay, x is an upper bound for E. Since B is the sup, since B is the least upper bound of E, we know that B is less than or equal to this upper bound, x, which contradicts what? It contradicts that x was less than b, that b was greater than x. So in either case, we've got our contradiction. What's the only choice that remains? B squared must be 2. So the square root of 2 doth exist. Let's do another lemma now. These lemmas are serving us well. If E is a subset of the integers, not empty, and bounded above. Now, by the way, I want to point out that all of these things that I'm proving for a set that is bounded above, all those things also work for the set being bounded below. Okay, so I'm not going to prove them both because the arguments are almost identical, just switching around inequalities. So keep in mind that we're actually proving two things at once. When we prove it for a set that's bounded above, you could put in below and change what you need to change. Okay, you change the sup to the inf, etc. So if E is a set that's bounded above, then the sup of E actually lives in E. So there exists a maximum of E. All right. Proof. Well, let B be that supremum. Okay, B is a sup of E. And suppose B does not live in E. So many of these are proved by contradiction. This is another one. Then let square brackets B, and you've seen this once before this semester, be the greatest integer less than or equal to b. Okay, so let's talk about the greatest integer function. Okay, if b is an integer, then the greatest integer less than or equal to b is itself. The greatest integer in 4 is 4. The greatest integer less than or equal to 4.2 is 4. The greatest integer less than or equal to 0 is 0. The greatest integer less than or equal to negative 1.6 is negative 2. So it's always the next integer to the left of the number or equal to the number. Does that make sense? So that's the greatest integer function, a very handy function in algebra. So let square brackets b be the greatest integer less than or equal to b. Okay. Now, the greatest integer in b does live in e, since no larger integer than this one, than the greatest integer in b, bounds e above. See, every larger integer would be bigger than b itself. And being bigger than b, if b is actually the sup of e, then as soon as I go to the next integer, I'm outside of e. Okay? And, of course, the greatest integer in b is strictly less than b. Why? Because if the greatest integer in b was equal to b, then b would be an integer. If b was an integer, it would actually be in the set e. And we're assuming that it is not. Okay? Similarly, now a little cliffhanger, because I need to erase the other board. What is it similar to? I need to know, and I need to know now. Well, boo-hoo. But you'll know soon. Okay. Similarly, let A be the nth of E. So we are going to go ahead and do the other one. Then A does not live in E. So similar result for the nth of E. We'll go ahead and prove them both. What the heck? So suppose that A is the nth of E. A does not live in E. Same argument as before. Then the greatest integer in A plus 1. Now, if A is the greatest lower bound of E, then A plus 1 the greatest integer in A plus 1 still bounds E below. that is strictly greater than A. Because remember that E is just a set of integers. So if A is an inf, and A is not in E, so it's not an integer, then I can go up to the next integer and I still have a lower bound. So, and of course, the greatest integer in A plus 1 is greater than A, which contradicts A being the greatest lower bound. So same argument underneath gives us both of them. So I ended up just being nice and doing both cases. Okay. Now there's a corollary to this, and I want to talk a little bit about the corollary. There are several results in mathematics, we've talked about this before, that cannot be proven. They're so-called axioms, but some of them are given other names. One of them is the axiom of choice, which says that if I have a whole bunch of sets, that it's possible to choose an element out of each set. That is equivalent to what's called Zorn's lemma, which says if every chain of things, if I have a partial ordering like less than or equal to or subset or something that is a partial ordering, then if every chain of things, that means they're telescoping. This one is less than or equal to this one, is less than or equal to that one, less than blah, 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 blah. If every such chain has an upper bound, then the whole collection has a largest element. Might have several largest elements, and that's no problem. But that's called Zorn's lemma. And lemma is not a great word for it simply because lemmas generally can be proven. And Zorn's lemma being equivalent to the axiom of choice, which cannot be proven, then Zorn's lemma can't be proven. Another one that is equivalent to those is the well-ordering principle. And we're going to do that next, but we're assuming that those kinds of things are true in the setup of the well-ordering principle. And let's attack it. It doesn't take long. So this is called the well-ordering principle. And it goes like this. Every non-empty subset of the natural numbers has a minimum element. Now, you could try to think of some set of natural numbers that doesn't satisfy that, but every time you come up with some set of natural numbers, it's generally pretty obvious what the smallest one of them is. And of course, the smallest natural number is 1. So it would be difficult, you might think, to come up with a natural number that is the smallest in just any non-empty subset of the natural numbers. And the reason that it's difficult is because if you assume that these other results are true, you assume that the well-ordering principle is true. It is impossible to prove it to be false. But from what we've had before, meaning that some of what we've had before required the axiom of choice, from the things that we've had before, we're able to prove it. So, and the proof is a mile long. It's going to take an hour and a half. No, it's one line. Proof. The subset is bounded below by, it's bounded below by 0, it's bounded below by 1, it's bounded below. So the inf exists for this subset and is, by the lemma, the minimum. It would take one line if I didn't put in all my extra words, but you know how I am. So, so much for the well-ordering principle. Now, the next theorem is the one that I was telling you about. The fact that the rational numbers are dense in the real numbers. That between any two real numbers, I can sandwich a rational number. That can actually be proven. We don't need that. That was for complex variables. Theorem. The set of rational numbers is dense in R, which is to say, if A is less than B in the real numbers, then there exists some rational number Q such that A is less than Q is less than B. Between any two real numbers, I can sandwich a rational number. And here comes the proof. First, I should say firstly, an adverb, there exists some natural number, little n, such that NA is bigger than B. For, suppose that we let E be the set of all integers such that k times A is less than or equal to B, E is non-empty. Right? And of course, why? Because 1 is in E. All right? 1 times A is less than or equal to B because A is less than B. Okay, so 1 is in there. Now, Ka is less than or equal to B implies that K is less than or equal to B over A. No big surprise, I'm dividing by a positive number. Let's see. Let's do this first for the positive real numbers. You can do this, put a little plus sign here. Okay, the positive real numbers to start with. okay? So that if I divide by A, I'm preserving that inequality. And this is for all K in my set E, because of the definition of E. So what does that mean? It means that E is bounded above by B over A. Therefore, by the completeness axiom, which we just proved, the soup exists. Well, let's give it a name. Let's call it K sub 0, okay? Now, by the lemma is something that helps prove a theorem. It's going to help prove this one. By the lemma, K sub 0 does live in the set. So K sub 0 is a natural number. Everything in E is a natural number. Okay? And it's no big surprise that K0 plus 1 is a natural number. And K0 plus 1 is greater than the soup of E, because it's bigger than K0. Okay? Therefore, K0 plus 1 is not an element of E, and thus K0 plus 1 times A, since it's not an E, this inequality must not be true. So K0 plus 1 times A must be greater than B. So let N equal K0 plus 1. Okay, there exists some number for which this is greater than B. Fine. Now we found it. All right. Now, the second part of this is, since B minus A is positive, by the above argument, meaning this, let's pick n in the natural numbers such that n times this number is greater than 1. And now, let E be the set of all integers such that K is greater than N times A. I'll hold on for a minute. Probably even less than a minute. See, that wasn't too bad, was it? Didn't give you enough time to order for pizza, but it wasn't too bad. Okay. So, E is bounded below by A. Okay, since A is greater than, let's see, bounded by, right, because A is below the set of all things that are bigger than NA, because N is a natural number. So it's bounded below by A, so the inf exists. All right. Now by the lemma, so it's going to help us again. Y is in E, so Y is an integer. Hence, M equals Y minus 1 is an integer. If Y is an integer, Y minus 1 is an integer. But since Y is in E, M plus 1, which is equal to Y, is greater than NA. E is a set of all the stuff that's greater than NA. Now we claim, that M is less than Y. Okay, now why would that be? Since if not, NA would be less than M, would be less than Y. So M would be in E. Thus, Y couldn't be a lower bound. For E. Okay, so what's the punchline to that? M is less than Y. Okay, now, since M is less than Y, we have M is less than or equal to NA. Okay, M is less than or equal to NA, which is less than M plus 1, and M plus 1 equals Y. And the fact that Y is greater than NA what does that imply? That Y over N is greater than A, just dividing both sides by N, and Y equals M plus 1 is less than or equal to NA plus 1, which we've already seen, which is less than NA plus N times B minus A. Okay, because I get something bigger if I multiply by N times B minus A than just 1. And that is equal to NA plus NB minus NA, which is equal to, and let's write it in there, that's equal to NB. Therefore, if I take Q to be Y over N is greater than A, and I get that this is less than B, Y over N is greater than A, and y over n is less than b. So A is less than Q is less than B. And that's what I had to prove. Okay. So with that little QED, we've proven a lot. You've filled your brains. And next time, we're going to start talking about the two different stages of infinity that we know about. As I've told you before, there are infinitely many different sizes of infinity. But we're going to talk about countable infinity, which almost sounds like a paradox, but it's not, and uncountable infinity. So until then, muchachos, muchachas, hasta la vista.